Now we come to module 2. In this module we will see about stress strain diagram. The stress strain diagram is obtained by conducting tensile testing of a test specimen. Test specimens are made as per standard available. This shows a schematic of the tensile test specimen. Here L0 is called the gauge length, and A0 is the nominal cross section or original cross section. Now in tensile testing, how it is done is the load P on the material shown here, the load on the material is gradually increased, and at each instant L and A are measured. What L is the length of the specimen and L is the length of the specimen and A is a cross sectional size. These both parameters are measured till the material fails, and we calculate the stress, which is nothing but the load divided by area. Here A is the nominal cross section area or original cross section area, and we have strain epsilon as change in length by original length. Change in length is L minus LO by L0, where L is the length at any instant of loading. Similarly, at each instant of loading, you find each instant of load P, you find the stress as well as the strain. So you can plot a table like this. You have P1 is a load, and sigma 1 and epsilon 1 are the stress corresponding to this load. Now you go to next load P2, find what is sigma 2 and epsilon 2, etc. You go up to Pn, the sigma n and epsilon n, where the material fails. Thus we have a series of sigma and epsilon values, and this sigma and epsilon values we plot against each other, then we get what we call as stress strain diagram. This figure shows a typical stress strain diagram for structural steel member. As I have mentioned above, when the stress and series of stress and strain values which we saw in the above example, when they are plotted against each other for structural steel, we get a diagram like this. This diagram has got several points at which the curve turns, and these points are very important to us. The initial portion OA is called the proportional limit, this is called proportional limit. As the name indicates, sigma, the stress, is proportional to strain in this portion, and we can say that sigma is equal to E into epsilon, where E is the constant of proportionality called the elastic modulus or the Young's modulus. Sorry. The different portions of this curve are mentioned here. The portion OA is a linear elastic portion, and the point A is called the proportional limit. Similarly, the portion AC is a yielding zone. What is yielding? Yielding is nothing but a significant increase in strain significant increase in strain with less increment in stress. This is called yielding. This is what happens in this portion A to C. In the portion BC, we can see that the stress is almost constant, but the strain keeps increasing tremendously. So this increase in strain with almost nil, very less amount of increase in stress is called yielding. And after point C, again the material gets hardened and you need to increase the stress in order to increase the strain. And the portion CD is called the strain hardened portion. And from D, the necking starts. Necking is nothing but reduction in cross-sectional area is called necking, and the necking starts from point D to point E, and at point E the failure of the specimen takes place. Now the stress strain diagram, now in this above example we have calculated the stress sigma based on the formula P by A, but A was nothing but the original cross-sectional area. Similarly, strain we have calculated as change in length by the original length, where L0 is the initial or original length. Such kind of a stress strain diagram, which is drawn based on the original cross-sectional area and original length, is called a nominal stress strain diagram. Or it's also called engineering stress strain diagram. Nominal stress strain diagram or engineering stress strain diagram. So when the nominal cross-sectional area and the original length are used for calculating the stress and strain, the corresponding stress strain diagram is called the nominal stress strain diagram. When we use original cross-sectional area and original length. Now similarly, if you use the instantaneous length and the instantaneous cross-sectional area, that is at each instant of load, if we calculate what is the area and the length, and the area and length at each instant of load is called the instantaneous area and instantaneous length. And if instantaneous area and length are used for calculating this stress strain diagram, then it is called a true stress strain diagram. True stress strain diagram. That is based on the instantaneous cross section as well as length of the specimen. So when I do a true stress strain diagram, I get sigma is equal to P by A dash, where A dash is the instantaneous cross section. And similarly, epsilon will be L minus LO by L dash. L dash is the instantaneous length. So that is difference between the true stress strain diagram and the nominal stress strain diagram. So in the figure shown here, we can say that O, A, B, C, sorry, I will repeat. So we have seen that for when the original cross-sectional area and original length are used for calculating the stress and strain, the corresponding stress strain diagrams Therefore, we have seen when the original cross-sectional area and original length are used for measuring the stress and strain, the corresponding stress-strain diagram is called nominal stress-strain diagram. Where original cross-section as well as length are used for measurement. But if we take instantaneous cross-sectional area and instantaneous length for calculation of stress and strain, that stress-strain diagram is called true stress-strain diagram. That is instantaneous cross-sectional area as well as length. When these parameters used for calculating the stress and strain, it's called true stress-strain diagram. So in this figure, we can say that O, A, B, C, D, E. This is the nominal stress-strain diagram. Whereas O, A, B, C, D dash, E dash is called the true stress-strain diagram. So that is about the stress-strain diagram for structural steel. Now, when we draw the stress-strain diagram for ductile materials like aluminium, it is shown here. The stress-strain diagram is different from that observed for structural steel. In structural steel, we could see that there is definite value of the yield stress sigma y, and the stress corresponding to point B is the sigma y yield stress, and the stress corresponding to point D is the ultimate tensile strength of the material. But in ductile materials like aluminium, we don't have a well-defined yield point. Therefore, what we tend to do is we use a method called 0.2% offset yield stress measurement. 0.2% offset estimation of yield stress. What is exactly done is we measure the mark a point here, this point to this point, this distance is nothing but 0.2% strain, that is 0.002. So we take a strain value of 0.002, mark this point and draw a line parallel to the which is parallel to the initial straight line portion. Where this line intersects the curve, the stress corresponding to that point is taken as a yield stress value. So yield strength value is nothing but stress corresponding to the point of intersection of the line parallel to OA, I will say initial line, passing through strain value is equal to 0.002, or I will say it's 0.2%. So this stress value is called the yield strength of the material for ductile materials like aluminium. Whereas for the structural materials like structural steel, we have seen that there is a well-defined yield strength, that is nothing but the stress corresponding to point B. And in ductile materials, we have now seen how to find the yield strength of the material by using 0.2% or 0.2% offset estimation. We can find out what is the yield stress. Similarly, the stress strain diagram for brittle material is something like this, shown here. For brittle materials, we can see that the stress keeps on increasing with respect to strain, and it just fails at one point where stress exceeds some ultimate tensile strength of the material. The difference we see from the ductile materials is that In ductile materials, even though it causes the ultimate tensile strength, it starts necking and starts elongating, the specimen starts elongating before failure. But in brittle materials, there is no elongation or there is no indication of failure. So we can say ductile materials okay, before coming to this ductile materials, I would like to stress upon two parameters called the percentage elongation. Percentage elongation is nothing but the final length minus initial length divided by initial length into 100. And percentage reduction in area is equal to final area minus initial area by initial area into 100. And based on this percentage elongation, the materials can be divided into two. Basically, ductile materials and brittle materials. So, ductile materials are those materials which elongate or undergo large strains. Undergo large strain before failure. Usually if the strain is greater than 5%, we say that material is ductile. And brittle materials are those materials which undergo very less strain. Before failure. Or we can say when the total elongation, the percentage elongation is, this is percentage elongation. If the percentage elongation is less than 5%, we say the material is brittle, and if the percentage elongation is more than 5%, we say the material is ductile. So for brittle materials, we have seen, we can see that it does not have any yield point. It just keeps on, the stress keeps on increasing with the stress, increasing with the strain, and at one point of stress it just fails without any indication. Therefore, since the brittle materials do not give any indication of failure, they are not preferred for the structural members. For structural members, ductile materials are preferred because they give an indication of failure. That is, after causing UTS, before failure it shows a large deformations or large elongations, telling that the material is going to fail, so that we have time to replace the material. Therefore, in most of structural application, ductile materials are preferred to brittle materials. Now, the strength of the material. This is one important concept. The strength of material, we say there are two types of strength. Two strengths are defined for materials. One is yield strength. One is ultimate tensile strength. Or we say it is UTS, and this is sigma y. And I have already mentioned that yield strength is the, for structural steel, yield strength is the yield strength of the material is a stress value corresponding to point B, and the ultimate tensile strength is the stress value corresponding to point D. And in ductile materials like aluminium, the yield strength is the stress value corresponding to this point, which is the intersection of the line parallel to the initial straight line and passes through a point where the strain is 0.002, and the maximum value of stress attained in the stress strain diagram is the ultimate tensile strength of the material. In brittle materials, we usually define the ultimate tensile strength only. So this is there's a fundamental difference between strength of the material and the stress in the material. Strength of the material is the inherent property in the material. Strength of the material is the inherent property of the material. whereas stresses are not inherent, these are induced in the material. And they are induced in the material due to the loading. Suppose I have a steel specimen with the yield strength of 300 megapascal and a ultimate tensile strength of 450 megapascal. When no load acts on member made of the steel, then I say when the load is 0, I say the stress on the member is 0, but strength of the member is 300 megapascal. What I mean is, it can take stress values up to a maximum of 300 megapascal without causing any deformation. And as we have seen in the proportional limit, we have already seen that the stress is proportional to strain, and we have derived the quantity called the elastic modulus of the material, which is nothing but E is the elastic modulus or the Young's modulus. Of the material. Similarly, we have the shear stress is also proportional to shear strain in this region, and the constant of proportionality is called G. That is nothing but the rigidity modulus or the shear modulus. G is nothing but rigidity modulus or the shear modulus. Now we see what is Poisson ratio. When a material is loaded axially, we have seen that it elongates in the axial direction like this. But in addition to elongation, there is a contraction in the lateral direction. That is, in the lateral direction, there is a contraction. So, if I take the initial specimen like this, after application of load, what happens is, this gets elongated, but it comes down. There is an increase in length in the axial direction, and there is a decrease in the length in the transverse direction or lateral direction. Decrease in length, and X is increase in length. And we defined a term Poisson ratio as nothing but minus of lateral strain to longitudinal strain. A negative sign is given because when you have a tensile load acting here as shown here, there will be the longitudinal strain will be positive because there is increase in length, but lateral will be a reduction in the length, therefore it is always negative. So when you have a negative, the total term becomes positive. That is why the negative term is included. So this means that the stress acting in a x direction can cause a strain in the y direction if this is my coordinate system. Now, if I have a three-dimensional body, as we have seen earlier, it has got normal stress in all directions. Then we can say the stress in x direction can be given as sigma x by E minus nu times sigma y by E minus nu times sigma z by E. or this can be written as sigma x by E minus nu by E into sigma y plus sigma z. Similarly, in the y direction the strain will be sigma y by E minus nu by E into sigma x plus sigma z. Similarly, in the z direction this is given by sigma z by E minus nu by E into sigma x plus sigma y. This relation, which connects the strain and stress in 3 dimensions, is called the generalized Hooke's law. Earlier which we have seen that sigma is equal to E into epsilon is just a one-dimensional case where you have stress and strain only in one direction, but in actual case you have stress and strain in all the directions. Even a stress in x direction can cause a strain in the y direction, as we have seen here. So in a generalized condition you have the generalized Hooke's law as this. Now we have seen that the two elastic modulus we have seen, one is elastic modulus, Young's modulus, and another one is a shear rigidity modulus or shear modulus. They are connected by the relation G is equal to E by 2 into 1 plus nu, and similarly K, which is nothing but the bulk modulus, is related to the elastic modulus as 3 by 1 minus 2 nu. So this is a very important relation which relates all the moduluses with respect to each other. The elastic modulus, shear modulus and bulk modulus are related to each other by these relations. Thus we have seen that the elastic modulus, shear modulus and bulk modulus are related to each other by the relation Eg is equal to E by 2 into 1 plus nu, and K is equal to E by 3 into 1 minus 2 nu. Similarly, we have also seen what are the generalized Hooke's law. Now we will take a small problem. Suppose Poisson's ratio of a material is given as 0.4. What is the ratio of shear modulus of elasticity to the Young's modulus of elasticity? What will be the ratio? From this equation here we can find out that G by E can be given as 1 by 2 into 1 plus nu. That will be here, it will be 1 by 2 into 1 plus 0.4, it will be 1 by 2.8. This is nothing but 5 by 14. So given the Poisson's ratio, we can find out what is the ratio of the different modulus, Young's modulus to shear modulus, Young's modulus to the bulk modulus. Similarly, you can find the ratio between different other modulus also. So with this we come to the end of module 2 on stress strain diagram. In the next module we will see now what are the kinds of stresses which are experienced by the machine members, which are subject to different kinds of loading. Again, for this module also the reference book is the same, by Timoshenko, Mechanics of Materials by Timoshenko. Thank you.